Good morning and welcome to GTC. My name is Tariq Hamidou. I am a Senior Developer Relationship Manager at NVIDIA, focused on AI retail intralogistics applications. I would like to introduce you to my co-presenter, Jeremy.
Thank you, Tariq, and thank you all for attending today. I'm Jeremy Jarrett with Kinetic Vision. Kinetic Vision is an NVIDIA service delivery partner, and we use digital twin technologies to solve product development and manufacturing challenges. We will be sharing an innovative approach for deploying highly accurate computer vision AI applications at the edge.
Thank you, Jeremy. It's great to be with you. Here is the agenda for today. First of all, Jeremy will be talking about the problem we are addressing and the business impact. Then I will be talking about the importance of IVA for retail and supply chain and highlight some use cases. In the third section, Jeremy and I will discuss the challenges of deploying computer vision at the edge and the importance of accuracy, quality, and security. Then, we will present how we are leveraging GPU technologies and different tools to deliver highly accurate models and applications. In the fifth section, I will discuss the deployment of those applications at scale. And finally, Jeremy will close the presentation by a conclusion and highlight what we are doing in the future.
Let's start by grounding ourselves on the problem. Let's talk about the retail supply chain. It is the process that you use to get your products to your consumers. It encompasses everything from obtaining raw materials, to making your product, to delivering that product into your shopper's hands. Understanding the value chain and defining each process will lead to efficiency and driving value across each step. Retailers today are investing billions of dollars to optimize this process by first identifying critical gaps and problems and then applying technology to achieve optimal results. Some of the most important parameters within a successful supply chain process are quality, accuracy, security, and throughput. Major impacts in each of these areas can be made through improving technology and automation. Let's try to identify one of the gaps and major problems. Let's narrow our view to cover the process of receiving goods and shipping goods. One of the main challenges retail and material handling face is picking the wrong pallet and incorrectly labeling, which leads to incorrect product sorting. This will lead to major issues within the material handling process, have a negative impact throughout, and in most situations lead to a decrease in customer satisfaction. Therefore, retailers need a highly effective method to label products and efficiently detect and classify products in order to avoid this problem. In summary, from a material handling perspective, here are some of the issues. Picking the wrong pallet or product, picking damaged packages, a very common problem within distribution centers. When dealing with a large number of SKUs, the sorting process can be extremely slow, leading to inefficient distribution and fulfillment center performance. Poor optimization of space and real estate, and the cost of ownership related to automation and deploying technologies for automated sorting. Within the context of this presentation, we're going to focus on video analytics solutions. Tariq, why don't you take it from here?
Now that we have an idea around the problem we are addressing, I would like to talk about intelligent video analytics. In the late 80s, companies began installing CCTV cameras to monitor the behavior of people in their buildings. One challenge for retail store owners and other property managers was the fact that there was an overwhelming amount of data, and it would be both unrealistic and inefficient to have people constantly watching and analyzing the security footage. The solution came from software engineers and data analysts who developed what we call intelligent video analytics. Video analytics is the capability of having software automatically analyzing video footage to detect and determine the type of spatial and temporal event. Utilizing AI, property managers are able to monitor and analyze their surveillance footage at a much larger efficiency, accuracy than ever before. Using IVA, Companies can determine how specific customers prefer to navigate the store and how long they take. This type of information is incredibly important since you can get very specific and determine if items and signs are prompting people to move faster and keep them engaged in specific areas. You can also determine if it is necessary to move shelves around and make certain areas more navigable by first recognizing specific patterns and then by analyzing those patterns and behaviors. Retailers can determine what actions need to be taken in order to decrease cost and increase revenue. This information can be vital to a company's financial planning, employee evaluations, marketing efforts, and overall business performance. We can extend this to the entire supply chain and specifically distribution centers and fulfillment facilities. Once you are able to determine which areas of your warehouse are generating the most traffic, you can work to optimize product distribution through the warehouse in order to thin traffic and make for more efficient experience. Through using video analytics, you can move certain products to other areas that experience lower traffic to better help your employees manage this product as well as limit customer wait time. Product detection and classification can lead to an efficient storage and retrieval process and a better shelf stock reconciliation. Within the material handling process, action recognition and activity recognition can help retailers and material handling companies set a high standard of operations and also implement proactive solutions for health and safety. Now that we have an idea on the benefit of IVA, let's discuss what it takes to build highly accurate IVA applications. Artificial neural networks and deep learning are powerful for designing state-of-the-art algorithms in computer vision. These architectures outperform traditional image processing and machine learning methods. Interestingly, our understanding of why and when these methods work remains limited. Designing a highly accurate computer vision models is an iterative and intuitive process consisting of selecting a model, training the model, and then deploying it. It's combining data science and mathematics with the art of putting together convolutional neural networks layers to form the model, and at last engineering the computer vision pipeline. Over the years, NVIDIA built powerful tools and SDKs to help developers build efficient AI applications and accelerate the deployment of highly efficient computer vision AI models. In addition, NVIDIA's partnership with developers lead to innovative solutions and products. In the next slides, I will summarize few important tools and SDKs part of our computer vision framework. DeepStream is a streaming analytic toolkit to build AI-powered applications. It takes the streaming data as input from USB CSI cameras, video from file or streams over RTSP, and uses AI and computer vision to generate insights from pixels for better understanding of the environment. DeepStream SDK can be the foundation layer for a number of video analytics solutions like understanding traffic and pedestrians in smart city, health and safety monitoring in hospitals, self-checkout, and analytics in retail. DeepStream offers exceptional throughput for a wide variety of object detection, image classification, and instance segmentations-based AI models. Another important SDK is TRT, or TensorRT. It's an SDK for optimizing trained deep learning models to enable high-performance inference. TRT contains a deep learning inference optimizer for trained deep learning models and an optimized runtime for execution. Once you have trained your deep learning network in any specific framework, TRT enables you to inference it with higher throughput and lower latency. Key technologies TRT implements that are highlighted in this slide: layers and tensor fusion, kernel auto-tuning, multi-stream execution, dynamic tensor memory, and precision calibration. In addition to DeepStream, to reduce development effort and increase throughput, developers can use highly accurate pre-trained models from Transfer Learning Toolkit, TLT, and deploy with DeepStream. The following table shows the pre-trained models. DeepStream is built for both developers and enterprises and offers extensive AI model support for popular object detection and segmentation models, such as the state-of-the-art SSD, YOLO, faster RCNN, and mask RCNN. You can also integrate OpenCV functions and libraries in DeepStream. Flexibility for rapid prototyping to full production-level solutions, and a greater flexibility by allowing you to choose your inference path. For example, with native integration to Triton Inference Server, you can deploy models in native frameworks such as PyTorch and TensorFlow, or achieve the best possible performance using the NVIDIA TensorRT for high throughput inference with options for multi-GPU, multi-stream, and batching support.
As most of you probably know, there are often some huge challenges when it comes to training vision models, and it often has nothing to do with machine learning algorithms. Considering that the data you use to train your model is likely the primary influencer on its performance, getting good data can often be a bear. Real-world data is difficult and costly to acquire, especially when people have to do the capturing and tagging. Manually created data sets are often confined by the constraints that come with the physical world. They are naturally limited in size, variation, and complexity to keep the costs and time under control. In the retail space, where SKUs are constantly being added and subtracted from inventory, the data needs to be constantly updated for those changes.
From the machine learning perspective, and within the context of object detection and classification, before we even start thinking about how to solve the problem, we need to find the data. The basic ImageNet dataset and other existing datasets will not help. It's a classification dataset, so it has labels like cat, dog, but it does not have bounding boxes. Manual labeling is now a much harder problem. Instead of just clicking on the correct class label, you have to actually provide a bounding box for every object. And there may be many objects on a single frame. Most of the effort is really on getting the data right. I am excited about this coming section. We will show you how developers are combining the different tools and the SDKs provided by NVIDIA to come up with innovative solutions to solve difficult problems and bring operational efficiency.
For our case study, we're going to focus on a warehouse conveyor system that is moving several product SKUs from inventory storage to fulfillment. There are many product SKUs that need to be identified and sorted for filling orders. It is also possible that there are damaged products that need to be rejected during the process. Our models will focus on product identification. To tackle the challenges in this case study, we will introduce the use of synthetic training data using the AIVision platform. AIVision uses a data scientist-friendly interface to automate the creation of synthetic data sets using GPU technology like RTX and PhysX. The workflow is straightforward. Generate your synthetic training data and train your models, test your model in a virtual environment, and evaluate your results and keep optimizing your system. As your model is optimized, deploy it in the real environment. So, what are some of the advantages of using this type of approach? Well, the generated data avoids issues with data starvation due to lack of data and labeling. You can also systematically create numerous angles, backgrounds, and lighting variations in product types. A digital twin can be used to virtually test various material handling conditions, as well as generate test data that can be used during model evaluation. GPU technology makes real-time lighting and physics simulation possible, allowing to hyperspeed the generation of large training data sets required for deep neural networks. In addition to using photorealistic environments to produce synthetic data, Many other training techniques are surfacing that further take advantage of synthetic data generation. For example, domain randomization using non-photorealistic environments was demonstrated by NVIDIA in 2018. This reduces the asset burden by not requiring photorealistic environments to be presented in the training data. We will be leveraging only domain randomized data for training our models. Other techniques have also been developed using synthetic training data. Improved performance by fine-tuning with real images, and generative teacher networks that continuously improve the model performance. Also, curriculum learning that allows for faster training and faster neural architecture search. The agility of synthetic data is amazing, and it's been a tool for discovering new techniques in the rapidly accelerating research field of artificial intelligence.
Digital twins can be a powerful tool, and what makes it very interesting is ray tracing technology. In 3D computer graphics, ray tracing is a rendering technique for generating an image by tracing the path of light as pixels in an image plane and simulating the effect of its encounters with virtual objects. So what we are really able to do today is to create high-fidelity photorealistic version of the real world, allowing us not only to do virtual deployments, but real-time process optimization, generating large synthetic data for testing and evaluation. Digital twin platforms allow different team members to cooperate. In the next slides, Jeremy will share with you how he used NVIDIA Omniverse, our multi-GPU real-time simulation and collaboration platform, to create a digital twin and solve the conveyor belt product sorting problem.
Synthetic data can be generated in many different ways. Any environment that can be simulated can be used to generate synthetic data. Anything from a simple spreadsheet to a full turbulent CFD simulation. You can also use GANs to generate synthetic data. What is important is that your data has been validated to real-world responses. GPU technology has a huge influence in the speed and scalability of these simulations, finally allowing for practical generation of large synthetic training data sets. NVIDIA Omniverse is a tool that can be used for building and maintaining digital twins. Many developer features in Omniverse allow for connecting your simulation data sources, such as 3D models, materials, and control logic. You can build custom applications and extend existing applications to make the development process as efficient as possible. AIVision provides a higher-level interface for non-developers to quickly run data experiments from a simple UI. It has convenient tools for analyzing the data variability and exporting to common data set formats like COCO. For our study, we're going to focus on warehouse conveyor systems that are moving several product SKUs from inventory storage to fulfillment. There are many SKUs that need identification and sorting for filling orders.
Digital twin solutions can represent many aspects of the warehouse material handling process, and including modeling different types of equipment. My excitement within this topic is the possibilities to model everything, including the physical parameters around conveyor belt, cameras, and other equipment. You add to this the compute power GPU technology is giving us today to simulate every single step of the material handling process. Within the context of the conveyor belt product sorting problem, I'm able to simulate different lighting conditions, increase number of products seen on each frame, increase the speed of the conveyor. Certainly a powerful solution. Let's move now to the synthetic data generator. Training deep neural networks for object detection using synthetic images is our main topic here. To handle the variability in real-world data, the system relies upon the technique of domain randomization, in which the parameters of the simulator, such as lighting, pose, object, texture, are randomized in a non-realistic ways to force the neural network to learn the essential features of the object of interest.
Now that we have a synthetic data generator for domain randomized data and a digital twin of our environment, we have the basic building blocks to start training our model. Most of you are probably familiar with this training process. We will use the synthetic training data for our training set and keep a holdout set for validation during model training. We will also generate a test set from our digital twin that represents the real-world conveyor system. After each generation of the model, we can evaluate its performance on the test set to see if we perform better or worse than the last generation. We can also incorporate conditions into our digital twin that might be very difficult to create on a real conveyor system, such as products falling over or unforeseen lighting conditions. One of the great things about this approach is that you can start doing your model development well before any of your hard equipment is commissioned and get a head start on learning how your model behaves to the conditions in the environment. You may even be able to influence your design, such as belt contrast, lighting, and camera position, to get the best performing physical setup for your model. Now that we've decided what data we're going to train and evaluate our model with, let's look at the tools we'll be using for this end-to-end implementation. We start with pre-trained object detection models within NVIDIA TLT, and we use transfer learning to train those models using domain randomized training data from AIVision. We also create test data from a digital twin assembled in Omniverse. The trained model is converted to a TensorRT model for inference on the NVIDIA Jetson NX. The Jetson is then used to evaluate both virtual and real product video feeds. Finally, for redeploying models and managing our inference applications at the edge, we use NVIDIA Fleet Command, which is in development for the Jetson platform. No deep learning presentations can get by without presenting some metrics. Our model was trained with 10,000 images, and we used a faster RCNN object detection model with a ResNet 18 feature extractor. We trained these models on an 8 V100 DGX, and we trained them for 15 epochs. The training time for each of the generations of our model was 40 minutes per model.
So far, we showed you how we combine different tools and SDKs to put together an efficient workflow. Now, let's talk about the core idea. Changing the strategy of how to randomize the poses and scales of synthetic objects can improve the results in mean average precision. Having this strategy driven by the performance of the network in a feedback loop is a simple, powerful method. A lot can be done here, including experimenting with mixing synthetic data with real data and having different strategies running in parallel.
Here we show the basic data flow of our architecture. We use the AIVision configuration to generate synthetic training data sets from AIVision. The sets are then used to train the object detection and classification model using NVIDIA TLT. The trained model is then deployed at the edge using the DeepStream SDK, and we also have a method to backpropagate the model loss to further drive optimization of the synthetic data and retrain an improved model.
Extending the concept by creating different instances of TLT running in parallel. Based on the performance of each network, we keep only the highly performing networks. The synthetic data generator works in cooperation with different networks with an objective to select the best. Once the network is selected, we can test on synthetic data and real data.
Using this framework, we can generate many data sets quickly and train many models. That allows us to create edge cases and scenarios that are difficult or impossible to explore in real life, and balance our classes properly and avoid situations of bias. We can also optimize our data set for the best model performance and training time. From these many models, we can locate our best performers and evaluate and deploy those final models. Now that we have trained several models and updated the synthetic data with each iteration, we have a well-performing model on the left that is running inference on a Jetson Xavier NX using a movie from the digital twin. The right-hand side contains a DeepStream video feed from our 8-lane test conveyor. Even with just 2 generations of synthetic training, the inference results are very good between both the digital twin and the real-life test.
So far, we spoke about training the network to bring accuracy. One of the most important elements within the work I am doing with Kinetic Vision is how can we deploy our accurate model at scale, and how can we efficiently and securely manage our applications. Fleet Command is the solution, a hybrid cloud platform for managing and scaling AI at the edge. NVIDIA Fleet Command is a centralized control system operating in the cloud using one-touch provisioning. Fleet Command pairs with NVIDIA edge computing devices. Once paired, Fleet Command securely deploys, manages, and scales AI applications across the entire infrastructure in minutes.
Okay, let's talk about what we learned and what we're going to do next. So, there are many benefits to using digital twins over traditional methods. Although digital twins may not be applicable in all situations, they easily have the potential to be 1/10 of the cost of a system developed with physical data. In a traditional approach, training data and AI model iterations are done using a physical system. That requires a physical twin of the actual system infrastructure or production interruptions. It requires physical test specimens and extensive photography of each inventory item. Inventory photography must be manually annotated, and new products and product variations are very difficult to accommodate. This all results in an AI system that might be overtrained for a singular use environment and is not scalable. In the digital twin approach, training data, AI model testing, and optimization are all done within a digital twin. Training data is created using an automated synthetic data pipeline, and new products and product variations are easily accommodated. This results in an AI system that is generalized and scalable. There are technical advantages too. A synthetic generator provides nearly unlimited data generation ability. It's much easier to generate statistical variation in your data. You also have the ability to study or correct for specific cases. You can address bias and class imbalance. And you have the ability to generate cases that are difficult to study in reality, like shingle packages or different lighting conditions. Data has the #1 impact on model performance, not architecture, not tuning, and not hardware. Synthetic data generation gives you the most controllable influence on the performance of your models. And synthetic data is highly scalable. The scalability of this virtual asset is only limited by your compute resources. I'd also like to touch on our future work, where we'll be focusing on accessibility, automation, and scale. We'd like to have tighter integration with TLT to enable no-code implementation, where you can push a button, generate a data set, and have a machine learning model just pop out the other side. We're also looking to do tighter cloud implementation so that we can satisfy peak scale needs or lower the friction for people to evaluate the platform. We're also going to be working on data parameter searches using automated tools like Azure ML, and then move on to optimization algorithms to eliminate data set and feature engineering traditionally performed by the machine learning engineer. We'd love to start integrating with a job scheduling system so we can manage jobs across multiple GPUs and multiple nodes, things like LSF or Slurm. We'd also like to push for continual dataset optimization, where we're maximizing machine learning training efficiency as the environment changes. That would be utilizing NVIDIA EGX and Fleet Command to read data from the edge, bring it back, and continue training of the model, and then redeploy those models back out in the field. And some of the experiments we want to start doing are extending this framework to other emerging techniques like knowledge distillation and generative teaching methods. I'd like to thank you all for attending our talk today, and Tariq, thank you for co-presenting with me. It's been an absolute pleasure.